All right, to get started with section 1.3, we're going to look at solving 3 by 3 linear systems. And really up until this point, we've only dealt with 2 by 2 linear systems, which include two equations with two variables, usually x and y. We found when solving these 2 by 2 systems, there's three basic methods to arrive at our solution. We could take an algebraic approach using substitution or elimination, or we could take a graphical approach by graphing the two equations and finding their point of intersection. There's also the possibility that we have some strange situations that pop up, such as the lines being parallel, which would indicate that our system has no solution, or that the lines coincide, which means they lie on top of one another and there's an infinite number of solutions. Today we're going to examine how all three of these methods can be used to tackle a 3 by 3 linear system. Let's go ahead and get started. Up top, an example of a linear equation in three variables would be 2x plus 3y minus c equals 10. And the solution to that linear equation is going to be written as an ordered triple. And it goes alphabetically. So x would come first, y would come second, z would come third. Some examples of some ordered triples to an equation with three variables would be 4, 2, 3, 5, 0, negative 10, and negative 2, negative 3, 3. Down below, you can see an example of what a 3 by 3 linear system looks like. Notice there's three equations and three variables, x, y, and z, which will make our ordered triple. Now that ordered triple is going to be the solution that satisfies all three equations within this linear system. It's important to note that when we're dealing with a 2 by 2 linear system, that's dealing in two-dimensional space, x and y. When we're dealing with 3 by 3 linear systems, we're now dealing with three-dimensional space, which is x, y, and z. Each equation is a plane in space. So to solve this third order system, or a 3 by 3 system as it's called, we are finding the point or points that are in all three planes at the same time. And recall that for lines, either they intersect in a point, are parallel, or the same line. Likewise, if we have three planes, either they intersect in a point, a line, they don't intersect at all, or they have the same planes. Therefore, we can solve a 3 by 3 linear system. We can expect to find that the solution is going to be a point, a line, no solution, or a plane. We're going to go ahead and consider these possible scenarios below. The graphical depictions below illustrate the possible outcomes of a 3 by 3 linear system as having one unique ordered triple, infinitely many ordered triples, or no solutions. Starting on the left, there is one unique solution when the planes intersect at one common point. Moving to the right at the top, there are infinitely many solutions when the planes intersect at all points along a common line. So in this first example, you can see that when three distinct planes intersect along a line, there will be an infinite number of solutions. In my second example, when two of the planes coincide, which means they're on the same plane, and they intersect with a third plane, there will be infinitely many number of solutions. And then in my third example, these three planes coincide, which means they all share the same plane, which means there, again, is an infinitely many number of solutions. And then finally, we have a scenario where there is no solutions to that linear system. In this first example, you could see that all three planes are parallel, which means there's no intersection point, and therefore no solution that satisfies all three equations in that 3 by 3 system. In my second example, two of the planes may be parallel. Again, there's no intersection point of the three planes altogether, and therefore there is no solution to the 3 by 3 system. And then finally, in our third example, these three planes are intersecting, but not in a manner that allows for an intersection point of the three planes. Now to get started with solving a 3 by 3 linear system, it's really no more difficult than when we were asked to solve a 2 by 2 linear system. It just takes a little bit longer. But essentially what our plan of action is to do is we're going to take that 3 by 3 system and try to reduce it down to a 2 by 2 system using elimination. Now, when you're going through the process, it's strongly encouraged that you take your time when writing this to keep it organized and neat. That way it's a lot easier for you to follow your work. Now, I've broken down the steps for you guys into 5 essential steps for solving a 3 by 3 system. Step 1 is to make sure it's in standard form. Step 2 is to pick 2 of the equations and eliminate one of the variables. So let's start by doing that. Here's my 3 equations. I'm going to pick 2 of the equations. Which 2 I pick are completely up to you. I usually end up picking the first 2. So I'm going to write negative 4x plus 2y plus z equals 13. And my second equation is negative 5x plus 3y plus 6z equals 4. And now, once I've picked those 2 equations, I need to solve for one of those variables. Which variable you pick is completely up to you. Maybe I want to get rid of the z's. So if I want to eliminate z, I need to multiply my top equation by negative 6. And when I do that, I get 24x minus 12y minus 6z equals negative 78. And on bottom, I have negative 5x plus 3y plus 6z equals 4. And when I add these 2 equations together, my z's cancel out, and I'm left with 19x minus 9y equals negative 74. Now, once I have that equation, I need to come back to my 3 original equations and pick 2 different sets of equations. So in this first example, I wrote the first 2 equations, the top and the middle one. Now maybe I'll pick the bottom 2 equations, which would be negative 5x plus 3y plus 6z equals 4, and negative 3x plus y plus 5z equals negative 5. And here's the important part. I have to eliminate the same variable as I did in the previous steps. So again, in that previous section, I eliminated z. So I need to eliminate z again. So notice in my first equation, I have 6z. My second equation, I have 5z. I'm going to multiply the top equation by negative 5 and the bottom equation by 6. So I get 25x minus 15y minus 30z equals negative 20. And on the bottom, I have negative 18x plus 6y plus 30z equals negative 30. And when I add those 2 equations together, I get 7x minus 9y, the z's canceled, equals negative 50. So now notice I have 2 equations that have 2 variables, x and y. So now I just took a 3x3 system and I was able to reduce this down to a 2x2 linear system. And to solve this, now I need to cancel out either the x's or y's. It's up to you. Maybe I want to get rid of the y's. So I'm going to multiply the bottom equation by negative 1. So I have 19x minus 9y equals negative 74. Negative 7x plus 9y equals 50. If I add those equations, the y's cancel, and I have 19 minus 7, which is 12x, equals negative 24. X has to be negative 2. So I just found x. Now, in order to find y, I can come back to one of these 2 equations and plug in negative 2 for x and solve for y. So maybe I pick this equation. 7 times negative 2 minus 9y equals negative 50. Negative 14 minus 9y equals negative 50. Add 14 to both sides, I get negative 9y equals negative 36. Divide both sides by negative 9, and I get y equals 4. So I just found x and y. I just need to find z. So I'm going to come back to one of my 3 original equations, and I'm going to plug in negative 2 for x and 4 in for y. So maybe I pick the top equation. Negative 4 times negative 2 plus 2 times y was 4 plus z equals 13. And I get 8 plus 8 plus z equals 13. 16 plus z equals 13. Z has to be negative 3. So I just found my ordered triple, which would be x is negative 2, y would be 4, z would be negative 3. And I'm going to ask that you guys write it like this every single time for your final answer. As I mentioned before, when solving systems of equations, there's certain situations that pop up where the variables will disappear. If that happens, that will be your indicator that this is a special case, which will result in either no solution if the statement is a false statement, such as 2 equals 8. We know that's false, so there is no solution that satisfies that system. Or if we get a true statement, such as 2 equals 2, 0 equals 0, then we have infinitely many solutions. Let's consider example 2. We have our 3 by 3 system. Here's my 3 equations. I need to pick 2 of them to get started with, so maybe I pick the first 2. And I need to eliminate one of the variables. Which variable you pick is up to you. Maybe I eliminate z again. So I'm going to multiply top equation by -2. So I have 6x minus 10y minus 4z equals 38. 5x minus y plus 4z equals -5. And when I add these two equations together, my z's cancel, and I'm left with 11x minus 11y equals 33. And now I'm going to pick 2 other equations. Maybe I'll pick the middle one and the last one. 5x minus y plus 4z equals -5. And 4x minus 2y plus 2z equals 2. And I need to eliminate the same variable. So I need to eliminate z. So I'm going to multiply the bottom equation by -2. I have 5x minus y plus 4z equals -5. And -8x plus 4y minus 4z equals -4. And when I add those equations together, I get -3x minus 3 plus 3y equals -9. So I've now just reduced this from a 3 by 3 to a 2 by 2. So I have 11x minus 11y equals 33, and -3x plus 3y equals -9. And now I need to eliminate one of my variables, either x or y. So maybe I choose to eliminate the x's by multiplying the top by 3 and the bottom by positive 11. So we have 33x minus 33y equals 99, and -33x minus 33y, plus 33y equals -99. And when I add these equations together, the x's cancel, the y's cancel, as well as 99 and -99. So you notice that the variables dropped out completely, but I'm left with a true statement. When that happens, that is your indicator that this is a special case of infinitely many solutions. That means no matter what I plug in for x, y, and z into that original 3 by 3 system, I'm always going to be reduced down to a true statement. So no matter what I plug in will work. And let's look at one more example. Example 3. Here's my 3 equations. Start by picking the first 2 if you want. And my second equation, 8x minus 2y plus 4z equals 7. And I need to pick one variable to eliminate. Maybe this time I want to eliminate the y's. So I'm going to multiply the bottom equation by -2. So there's my top equation again. Bottom equation is -16x plus 4y minus 8z equals -14. If I add those equations together, the y's drop. And I'm left with -14x minus 7z equals -11. And now I'll pick 2 new equations from my original 3. Maybe I pick the middle and bottom again. 8x minus 2y plus 4z equals 7. -4x plus y minus 2z equals -14. And I need to eliminate the y's again, so I need to multiply the bottom equation by 2. So I have 8x minus 2y plus 4z equals 7, and -8x plus 2y minus 4z equals -28. And when I add these equations together, the x's cancel, the y's cancel, the z's cancel, and I'm left with 0 equals -21, which we know is a false statement. Therefore, there is no solution that will satisfy this given 3 by 3 system.